All right, welcome back to gas laws video 3. Today what we're going to do is we're going to talk about a couple of the gas laws, how pressure and volume relate to each other. Now, one of the things that we have to consider is that if we're going to look at pressure and volume and how they vary, we have to consider keeping temperature constant. So the molecules that are in the container aren't going to get warmer and go faster. The other thing that we have to consider is the number of molecules in the container have to stay constant. And so if we look at our particular blue container here, and we have these 5 molecules that happen to be flying around our container, and so we're going to give them a little temperature, so that one's going that way and that one's. One of the things that we have to also think about with gases is they randomly fly around, and they're all going to have some sort of velocity in some direction. And we're also going to assume that when they run into each other, they elastically bounce off in opposite directions. Now, if we look at this relationship of pressure and volume, and so if I go over here and I look at this, all this sign here means is how do these two things compare? So keeping everything else constant, if we look at a volume change, so I start to decrease the volume of this container. Pressure is the force per unit area. And so if we look at the size of the container, the area is decreasing. And so if the area decreases but the collisions are the same, what we get is an increase in pressure. So the smaller the container, the higher the pressure is going to be. And as we drag this thing out, what we realized is that the larger the volume, the lower the pressure is going to be. And so that relationship typically is called an inverse relationship. As one thing goes up, so if I write down here, as pressure increases, then volume will decrease. Okay? And so that, like I said, that relationship between these two is inversely related. Now, if we look at an equation for inverses that you might see in mathematics, it would look something like this, where it would say, you know what, if we want to look at pressure, pressure is equal to some constant divided by the volume. And so if we rearrange this so we get the constant all by itself, we're going to say that pressure times volume is equal to that constant. And that constant, it could be 10, it could be 100, it could be 1,000. It really doesn't matter what that number is at this point. What we realize is that for pressure times volume to equal that constant, if one increases, then the other one better decrease. Now we have a couple situations. Right now you can see our container has a certain volume. And so what we'll do is we'll say, you know what, the pressure in that container right now we'll call pressure 1, and the volume in that container is going to be pressure or volume 1. And it's going to be constant. If I go up and grab my container and I expand it, we're going to call this pressure 2 and volume 2. Those two are also equal to that constant. So if they're both equal to the same constant, then we should be able to substitute in and say, you know what, if I know the pressure of the situation in situation 1 and the volume in situation 1, and maybe I know the volume in situation 2, then I should be able to calculate my pressure. That's a P, by the way. My pressure in situation 2, and by just knowing my volume. So this is an inverse relationship, but what we can do is we can actually calculate from an initial situation, we can change the volume and say, you know what, I believe that the new pressure will be this. And so one of the things that we'll experiment with in this class is this relationship. Now, this is actually called Boyle's Law. And so if we look at the pictures below here, what we're doing is we're keeping the same number of atoms, same number of molecules in the container in both situations. But what we're doing is we're taking, here we have a pressure of 1, here we have a pressure of 2. So if we double the pressure, in other words, I'm pushing down twice as hard over here, then my volume is going to get cut in half. So if we did the math for this, we could say, you know what, in situation one, so this is my pressure, and we're going to call it pressure 1 times our volume. Let's make up a volume. Let's call it 20. And we can make it milliliters, liters, whatever we want to make it. Let's call it liters. Is equal to, and they're saying pressure 2 because we have this weight, this mass that's putting a double the pressure on. So we say 2 times what's our new volume. And so to do the math for this, all we need to do is simply divide both sides by the 2. And so I divide this by 2, divide this side by 2, and we take 1 times 20 divided by 2, which gives me 10 liters is equal to basically situation 2. Now, graphically, what you're going to see is as the volume expands, so this bottom is volume, this side is pressure, and what's happening is as the volume expands, the pressure is going to get smaller and smaller and smaller and smaller. Again, as the pressure gets smaller, the molecules are getting shoved into a smaller and smaller region, so the pressure is going to increase significantly. So Boyle's law basically says this right here, that pressure of situation 1 times the volume of situation 1 is equal to the pressure of situation 2 times volume of situation 2. And so when we start to do calculations, our units have to be the same for pressure. So if we have millimeters of mercury, then they both have to be in millimeters of mercury. Our volume has to be in the same units. If we have milliliters, then they both have to be in milliliters. Okay, so some things to pay attention to as you do calculations. Now the second thing we're going to look at is temperature and volume. Now this time we have to keep our moles constant, but what we have to do is also keep our pressure constant. So in the first scenario, if we have a point and that's its velocity, that gives us our temperature of that molecule. But if we double the temperature, what's going to happen is that thing is going to be moving faster. So in this particular case, if we have these little molecules that are flying around at a certain temperature, if we double their temperature, they're going faster, so they're going to tend to collide with the walls more often. Well, to keep them from increasing pressure, then we're going to need to increase the size of the container. And so if you think about this particular scenario, if the temperature rises, then the relationship of volume, the volume also has to rise. And that particular situation is called a direct relationship. And you guys have all done this in Algebra 1. You've done it. We're dealing with the lines. A typical equation of a line is y equals mx. Well, in our particular case, we're looking at volume is equal to a constant, we'll call it the slope, times temperature. Okay. Now, in temperature, the problem is if we have a negative temperature, it doesn't work. So we have to work in the absolute scale, which is called Kelvin. Now, Kelvin, if we look at Kelvin related to, say, Celsius, 0 Kelvin is equal to negative 273.15 degrees Celsius. So, alternatively, we get 273.15 Kelvin is equal to, is equal to 0 degrees Celsius. It's a 1 degree change. For every 1 degree change of Celsius, you get 1 Kelvin change. So, taking this back to this idea, if I want to solve this for the constant like we did in the last problem, what I'm going to do is I'm going to get T off that side. So I get V over T is equal to K. Now, again, we have two situations. The first situation says, you know what? We have situation 1, V over T, V1 over T1 is equal to K. And we have situation 2. So we'll say V2 over T2 equals K. So if those are both equal to the same K, then I should be able to say that, you know what, V2 over T2 is equal to V1 over T1. And so what we can do is, having this equation, we now can solve these problems of temperature and volume. Next, we'll talk about temperature and pressure.